This is a video series on temporal difference methods and reinforcement learning. I'm Chandra Sripada. In the previous video, I introduced the calendar problem and temporal difference methods. In the current video, I'll apply a version of a TD algorithm to solve the calendar problem in a more detailed way. Let's get started. So here was the calendar problem. I have already initiated the state values to 0. Recall that these state values are predictions of the cumulative expected reward that you're going to get over the course of the entire calendar. I also introduced this notation, and I introduced a temporal difference algorithm with 2 steps: calculate the prediction error and update the value of v parentheses s. If any of this is unfamiliar, go back to video 1. Keep in mind that over here I have probabilistic rewards. In this version of the calendar problem, to make things easier, I'm going to make these rewards non-probabilistic. You're going to get these rewards. If you enter February, you'll get the reward of 2 100% of the time. Because now the rewards are certain, I'm just going to get rid of the 100% showing on the screen as well. So it says round 1, and that indicates the first time we step through the calendar, we'll step through the calendar more than once. We start off in January, and we transition to February. Our current state is in orange. The previous state is in this kind of purple color. So what do? Well, I calculate the prediction error. And this should seem awfully familiar because it's exactly what I did in video 1. The reward and the value for state S prime are shown here. The value for state S is shown there. The prediction error is 2. Alpha is 0.5 throughout this example. So if I didn't mention that before, let me make that clear. I'm using an alpha of 0.5 throughout this example. And when I multiply the prediction error by alpha and I add that to my previous value for the previous state, that is the old value for the previous state, my new value for the previous state is 1, and I'm indicating that updating this way. Now I transition from February to March, and I step through this again. The prediction error in this case is 0. 0.5 multiplied by 0 added to the old value is still 0. So that's my new value also for the previous state. Now I transition from March to April. Here the prediction error is 4. The updated value for the previous state is 2. And now I'm just going to go more quickly because I think you've got the hang of how to apply these 2 steps to every single transition. April transitions to May, and April is now the previous state, and this is what the update looks like. And here I've transitioned to June, transitioned to July, to August, to September, to October, to November, to December. So that completes round 1 iterating through the calendar. And what it looks like is that the rewards, half of the value of the reward is being moved backwards to the previous state. So the state values of the state that immediately precedes the reward is now half the value of the reward. And the reason why it's half is that alpha has been set to 0.5. Now I'm going to go on to round 2. And again, I'm going to go fairly quickly. And you can hit pause anytime you have a question about how I arrived at the updates that are being shown here. So January is getting updated to 1.5. I transition to March, and February is getting updated to 1. Here's the transition to April, to May, to June, to July, to August, to September, to October, to November, to December. And I'll just make some observations. Notice that September used to be 5, and now it's up to 7.5. It's approximating the reward in October more and more. And notice August used to be 0, and now it's been increased because it's inheriting some of the value for September. Okay, so Here's a little summary of what happened. We started here with everything at 0. After round 1, that's where we were. And after round 2, here's a little bit of a typo. After 2 rounds, here's where we were. You can see a pattern kind of emerging. States with reward in them, like October, are generating or causing states that predict the reward in October to have increased value. Initially, it's the state immediately preceding October that gets some of the reward that October has. After the second round, now it's August that is getting some of the value that originates from the reward present in October. If we iterate this again and again, here's what's going to happen. After 20 rounds, the states that are predictive of future rewards are going to get higher and higher state values until these state values that were generated just by repeatedly applying the temporal difference algorithm, these state values approximate the true state values just after 20 rounds. That's pretty remarkable. Let's say that you had probabilistic rewards. Remember, I got rid of those. If I applied this temporal difference algorithm, after 20 rounds, here's what the state values look like. And here's what the true state values look like. Notice that these state values look pretty similar to the actual true state values. The algorithm doesn't change at all. You just do your updating with respect to a reward that sometimes appears and sometimes does not appear. And the state values will capture the probabilistic nature of the reward. And so even without you doing anything differently, your state values that emerge by application of the temporal difference algorithm start to approximate the true state values, even in a regime with probabilistic rewards. Let's say you have discounting of the future, so that a reward that is received, a reward, let's say, of 10 that is received in October has just 0.8, that is 80% of the value if it's received in September. In that case, what you do is you make a small modification to the calculation of the prediction error. Whereas previously, the calculation of the prediction error was the reward of state S prime plus the value of state S prime minus the value of the previous state, you multiply the value of the state S prime by this gamma coefficient that reflects the level of temporal discounting you're going to do. That's all you do to modify the algorithm so that now it's calculating for you the discounted expected reward. It's also, of course, doing probabilistic rewards because, like I said in the previous slide, you don't modify the algorithm at all to capture the probabilistic nature of the rewards. So here's your original start point, and you're a discounting agent. After 20 rounds, this is what your assignment of state values looks like. And here's what the actual state values look like. Notice that's a pretty complicated thing to calculate the probabilistic discounted rewards in a state space like this. And yet, the very same simple algorithm that's just applied repeatedly is calculating those probabilistic discounted state values. How could you solve this problem without using temporal difference learning methods? How could you solve a calendar problem like this with probabilistic rewards and discounting if you didn't have temporal difference learning? Well, here's a possible approach. Let's say you step through the calendar, say 5 or 10 times, and you took very careful notes in like a diary of what rewards were received in what months. At the end of all that, so at the end of 5 or 10 years, you look through your years of notes and you calculate the average reward you received for each month. And then you try to calculate the state values, taking into account the probabilistic and discounted nature that needs to be reflected in these state values. You know, that seems like a hard thing to do. First of all, you need to store 5 or 10 years worth of notes. You need to do some highly demanding calculations because you're calculating over all those notes simultaneously. And then you don't even get your state values until 5 or 10 years. With the TD learning method that we talked about, none of this is true. You just simply apply a very simple computation again and again, and you avoid all of these problems. Turn now to the question of why does temporal difference learning work? Here, what I'm showing is the simple calendar problem without probabilistic rewards and discounting. This is the version of the problem that we spent a lot of time going over in this video. And what we found is that after 20 rounds, the state values start to approximate rather nicely what the true state values are. And what we noticed is what is going on is that the reward present in a state, for example here in October, is getting passed backwards in the form of value to previous states that predict the states that have reward. But in addition, states that have value, that value is passed backwards to states that precede and predict the states that have value. So why does August have high value? Well, because it's predictive of a state with high value. You can see here for March, its high value owes in part to a state that it predicts that has high reward, that is April, as well as the fact that April itself has high value in virtue of predicting further states, again, with high value and potentially reward. So it's this kind of recursive process where value and reward are getting passed backwards. That's part of what explains why TD, temporal difference methods, are working. Here's another perspective. Here are the true state values for this version of the problem. We saw that earlier. Notice this, and if you need to, hit pause and spend some time noticing that this equality holds. This is a version of what's called Bellman's equality. And what it's saying is that if you look at every preceding state, a state S, and a subsequent state, a state S prime, when you do have the true state values, the preceding state always equals the reward of the subsequent state plus whatever state value attaches to that subsequent state. So September is 10 because October's value is 0 and its reward is 10. Look at March. Its value is 16 because April's reward is 4 plus its value is 12. That equality has to hold given the way that we've defined what state values are. This equality has to hold when we do in fact have the true state values. So if that's the case, then look at the role that Bellman's equality plays in our prediction error. The prediction error calculation itself is just the terms of Bellman's equality. The reward of state S prime plus the state value of state S prime are summed, which is just this term right here, and this state value of the preceding state is just that term right there. So what you are doing when you're calculating a prediction error is you're calculating how much you deviate from the conditions of Bellman's equality that need to hold when you do have the true state values. That prediction error, then when you do the updating of the value of state S, you just take a step towards reducing that deviation. How big of a step depends, of course, on the step size, alpha. So that's another perspective on why temporal difference learning works. Okay, this concludes video 2, in which we used a TD algorithm in detail to solve a version of the calendar problem. Now that we have a good sense of how the TD algorithm works and why it works, we're now in a great position to transition over to the reinforcement learning problem.